Chapter 5 From Violins to Videos. It has become conventional, as I have noted, to separate mathematics into two distinct subdisciplines labeled pure mathematics and applied mathematics. This is a separation that would have baffled the great mathematicians of classical times. Carl Friedrich Gauss, for example, was happiest in the ivory tower of number theory, where he delighted in abstract numerical patterns simply because they were beautiful and challenging. He called number theory the queen of mathematics. However, he also calculated the orbit of Ceres, the first asteroid to be discovered. Soon after its discovery, Ceres passed behind the Sun, as seen from Earth, and could no longer be observed. Gauss made several major innovations, some of which remain in use to this day. It was a virtuoso performance, and it made his public reputation. Nor was that his only practical application of his subject. Among other things, he was also responsible for major developments in surveying, telegraphy, and the understanding of magnetism. This chapter deals with a case history of just such a development, whose most powerful application is television, an invention that arguably has changed our world more than any other. It is a story in which the pure and applied aspects of mathematics combine to yield something far more powerful and compelling than either could have produced alone, and it begins at the start of the 16th century with the problem of the vibrating violin string.
In 1714, the English mathematician Brooke Taylor published the fundamental vibrational frequency of a violin string in terms of its length, tension, and density. In 1746, the Frenchman Jean Leron d'Alembert showed that many vibrations of a violin string are not sinusoidal standing waves. In fact, he proved that the instantaneous shape of the wave can be anything you like. In 1748, in response to d'Alembert's work, the prolific Swiss mathematician Leonhard Euler worked out the wave equation for a string. Also, Euler formulated the wave equation and solved it. His solution can be described in words. First, deform the string into any shape you care to choose, a parabola, say a triangle, or an irregular curve of your own devising. Then imagine the shape propagating along the string toward the right. Call this a rightward traveling wave. Then turn the chosen shape upside down and imagine it propagating the other way to create a leftward traveling wave. Finally, superpose these two waveforms. This process leads to all possible solutions of the wave equation in which the end of the string remains fixed. As their understanding of wave equation grew, the mathematicians of 18th century learned to solve the wave equation for the motion of drums of variation shapes. But now, the wave equation began to move out of the musical domain to establish itself as an absolutely central feature of mathematical physics. And then it showed up in the theories of electricity and magnetism and changed human culture forever. Their story begins with William Gilbert, physician to Elizabeth I, who described the Earth as a huge magnet and observed that electrically charged bodies can attract or repel each other. It continues with such people as Benjamin Franklin, who in 1752 proved that lightning is a form of electricity by flying a kite in a thunderstorm.
Luigi Galvani noticed that electrical sparks caused a dead frog's leg muscles to contract, and Alessandro Volta who invented the first battery.
Faraday was no mathematician, but his intellectual successor, James Clerk Maxwell, was. Maxwell expressed Faraday's ideas about lines of force in terms of mathematical equations for magnetic and electric fields. That is, distributions of magnetic and electrical charge throughout space. By 1864, he had refined his theory down to a system of 4 differential equations that related changes in the magnetic field to reveal a curious symmetry between electricity and magnetism, each affecting the other in a similar manner. It is here, in the elegant symbolism of Maxwell's equations, that humanity made the giant leap from violins to videos. A series of simple algebraic manipulations extracted the wave equations from Maxwell's equations, which implied the existence of electromagnetic waves. Of course, violins are accidents of human culture instead of European culture, but vibrations of linear objects are universal. They arise all over the place in one guise or another, among the Arachid aliens of Betelgeuse. It might perhaps have been the vibration of the thread on the spider wave created by a strangled insect that led to the discovery of electromagnetic waves. The next time you go to jogging wearing a Walkman or switch on your TV or watch a videotape, pause for a few seconds to remember that without mathematicians, none of these marvels would ever have been invented.